Hello! In this video, we are going to prove the following theorem. Suppose R is a relation on A. Then, R is reflexive if and only if the identity relation on A is a subset of R. Now, before we begin this proof, I would like to write some notes down. First of all, what does it mean for R to be reflexive? Well, if you recall, all that means is, for every element x in A, we have that x comma x is in R. And now, I would like to write some facts about the identity relation. Now, from the definition of the identity relation, there are two important facts. The first being, for every element x in A, we have that x comma x is an element of the identity relation on A. As for the second one, first of all elements in the identity relation are ordered pairs, right? Because the identity relation is a relation. So it turns out that for any element x comma y in the identity relation on A, it follows that x is equal to y, and they're elements of A. Right? Just like that. So now, we're going to go into our proof. Now, we're trying to prove a statement containing if and only if, which means we want to prove that if this is true, then this is true. And if this is true, then this is true. Let's start by proving if this is true, then this is true. To do so, assume this is true. Now, what does it mean for R to be reflexive? It means for all elements x in A, we have that x comma x is in R. And so our whole goal now is to deduce that this is true. We're trying to prove that everything in the identity relation on A is also in R. So to do that, let's consider an arbitrary element of the identity relation on A, say x comma y. What does it mean for an ordered pair to be an element of the identity relation on A? Well, from fact number 2, this means that the two coordinates are equal to each other and they're elements of A. So really we have that x is equal to y and they're elements of A. So now we have that x is an element of A. But because R is reflexive, we know that this means that for all elements x in A, x comma x is an element of R. So since x is an element of A, we know that this statement is true for the case of x in our proof. So we can replace the x here with x in our proof. So we have that x comma x is an element of R. But x is equal to y, so we can replace the second coordinate with y, and we get that x comma y is an element of R. So notice, we started with an arbitrary element, x comma y, in the identity relation on A, and we showed that same element was also in R. So this means that everything in the identity relation on A is also in R. And so this proves that if this is true, then this is true. Now we're going to prove if this is true, then this is true. To do so, assume this is true. So really, we're assuming that everything in this set is also in this set. And our whole goal is to deduce that R is reflexive, which means we want to prove that this statement is true. Now, we're trying to prove a statement about all elements in A. So give me an arbitrary element in A. I'll call it x. And now from here, we want to show that x comma x is an element of R. Now to start, since x is an element of A, we can use fact number 1 from the definition of the identity relation on A, right? If you recall, for all elements x in A, x comma x is an element of the identity relation on A. So since x is an element of A, this statement is true for the x that we have in our proof. So we can conclude that x comma x is an element of the identity relation on A. But the identity relation on A is a subset of R. So since x comma x is an element of the identity relation on A, it must also be in R. So at this point, notice that we started with an arbitrary element x in A, and we deduced that x comma x is an element of R. So since x was arbitrary, this means for all elements x in A, x comma x is an element of R. So we have proven precisely this statement, which amounts to proving that R is reflexive. And so now we have proven that if this is true, then this is true. So now we have proven both parts of the if and only if, which means we've proven the theorem. So this completes the proof. And so yeah, that's pretty much the idea of how you could prove something like this. And that's pretty much it for this video.